Our previous examples involved single deposits or withdrawals, so we were using the tables for single sum factors. Now we're going to change gears and discuss annuities. As you probably recall, an annuity is a series of equal periodic payments, and those payments occur with equal amounts of time between them. There are several different types of annuity situations. We'll be focusing on two types: ordinary annuities and annuities due. You have an ordinary annuity when the first cash payment occurs at the end of the first compounding period. You have an annuity due situation when the first cash payment or withdrawal occurs at the beginning of the first compounding period. Anytime you recognize a situation as involving annuity, the next thing that you want to do is make a determination as to which of these two types of annuities you have in that situation. Well, let's start with a really simple example here. We have an accounting student. The student wants to accumulate enough money that the student can pay for a master's program and earn the 150 hours that are required for accounting certification. The student's plan is to make $10,000 deposits at the end of each year for 3 years. So we recognize that as an annuity. We have 3 $10,000 deposits at equal intervals. The interest rate that the student thinks can be earned is 10%, and the question is, how much will the student have after 3 years? So we know the annuity amount, abbreviated PMT for payment. It's $10,000. The interest rate is 10%, and we have annual compounding here. So the number of compounding periods is 3 years. What we don't know is the future value. Because the payments are going to occur at the end of the year, this would be an ordinary annuity, and sometimes you hear that referred to as an annuity in arrears. They mean the same thing. Well, what's your guess as to what the future value would be? We know that it's going to be more than 30 grand, right? Because there's 3 payments of 10,000 each, plus that money has time to earn interest. The different payments have varying amounts of time for which they'll be earning interest. Let's look at a timeline here. The first annuity payment occurred at the end of period 1, the second occurred at the end of period 2, and the third occurred at the end of period 3. And we want to know the future value of those 3 payments. Notice that the payment at the end, the payment for period 3 has no time to earn interest because it occurred at the end of period 3. The first payment of $10,000 has 2 full years to earn interest. The second payment has 1 year to earn interest, and the third payment has no time at all to earn interest. So if we do the computation manually using just present value factors, as if these were just, we can compute the future value of each of these 3 payments and then add them all together, we would do it this way. The factor for 10% and 2 compounding periods is 1.21, so that $10,000 would turn into $12,100. The second payment of $10,000, we'd use the factor for 10% 1 period, it would turn into $11,000, and the third payment would just be $10,000. If you add them all together, you have $33,100, and that's the future value of that annuity of $10,000 per year for 3 years. If we didn't have equal payments, then this would be the way you would have to solve the problem, just doing separate future value computations and adding them up. But since it's an annuity, there are actually factors that take all of this into account for us. Excel, of course, can do the same thing. If you know the annuity amount, you know the interest rate, and the number of compounding periods, and you want to know the future value of that annuity, you multiply the annuity amount times the future value factor of an annuity, an ordinary annuity. So you'd go to the future value of an ordinary annuity table, use the table the same way we did previously, use the column for 10%, the row for 3 compounding periods, and you can see here that the factor was 3.31, and we get the same answer that we did a minute ago when we did a manual computation. Let's take a look at another example here. We have Plus Company. They're depositing $2,000 every quarter into a savings account. The first deposit is at the end of the current quarter, so this is an ordinary annuity situation. They do that for 5 years. They're trying to save money so they can buy this specialized machine. They'll be earning 12% annual interest, and once again, it's a future value of an annuity question because we want to know how much those 5 payments will accumulate to at the end of 5 years. So you'd go to your future value of an ordinary annuity table. You'd look up the factor for 3%, 20 periods. It's quarterly compounding, so you divide the interest rate by 4 and multiply the number of years by 4 and turn it into quarters. So it's 3% interest per quarter, 20 quarters, and you can see the factor here. You use the factor by multiplying it times the annuity amount. 2,000 times our factor gives us 53,741. In Excel, you use that same future value function that we looked at earlier. Now you do want to have an input here for payment. The annuity amount is what you put for the payment. Here it's going to be minus $2,000. Since this is an ordinary annuity, the type is 0. When you put this input in to the future value formula, you will get as an answer our 53,741. Now let's consider present value of ordinary annuity situations. This type of problem is asking, what's the value today of a stream of cash flows in the future? For example, how much would you pay today to get $1,000 a year for the next 5 years? Well, you know you would pay less than $5,000 because you have the ability to earn interest. $5,000 in the future is worth less than $5,000 today. For example, depending on the interest rate, you might be able to deposit $4,500 today and have $5,000 at the end of 5 years. Of course, we can word these questions in a number of different ways. There's a couple of other examples in the bullet list there. How much would you have to invest today to make a series of equal future withdrawals? Or, you can afford a certain amount of car payment for the next few years. How much car can you afford to buy for those payments? As before, when you're trying to determine the present value of an annuity, you have to ask yourself, is this an ordinary annuity or an annuity due? If the payments occur at the end of the period, you have an ordinary annuity. Take a look at this example. We have another accounting student. This student inherited some money. She intends to set aside enough of that inheritance to cover her last 3 years of living expenses and tuition. She wants to be able to withdraw $50,000 at the end of each year for 3 years. So there we know we've got this $50,000 annuity amount. The interest rate is 10%, and how much, the question we're trying to answer here, is how much of that inheritance does the student need to set aside today in order to be able to make those 3 $50,000 withdrawals. We know the annuity amount, the interest rate, and the number of compounding periods. What we want to know is the present value of those 3 payments of $50,000 each. We know that because of the particular timing described here, this is an ordinary annuity. And finally, we know that the answer is going to be less than $150,000 because 2 of those annuity payments are going to have time to earn some interest. Once again, we could solve the problem by setting it up as 3 separate problems. We could compute the present value of this payment for 1 year, this payment for 2 years, and this payment for 3 years. If you do that math, you can look up the factors and do the math and add them up. You'll see that you'll get the same answer that we're getting using the present value of an ordinary annuity table. These factors add up to 2.48685, and that's what the present value of an ordinary annuity factor is for 10% in 3 years. You use the factor the same way we did with our future value example. Multiply the annuity amount times the factor, and we get 124,343. If the student deposits $124,343 today, she will be able to take $50,000 out a year for 3 years. So she'll be able to withdraw a total of $150,000. The difference between the $150,000 and the $124,343 is interest that would be earned on those annuity amounts. We can prove our answer by doing a little amortization schedule like I have here. So here's the initial deposit that the student would make today. At the end of year 1, well, during year 1, let's start there. During year 1, that deposit would earn 10% interest. So 10% times 124,343 is, of course, 12,434. That gets added to the account. The student withdraws the $50,000 that she needs at the end of year 1. If you take 124,343, add the interest, subtract the withdrawal, you'll see at the end of year 1 there's $86,777 in that account. Follow through with the same math. Add 10% of that $86,000 as interest. The student withdraws $50,000 at the end of the year. Now there's $45,455 left in the account. That $45,000 earns interest. The student makes the final withdrawal, and there's no money left in that account. So we've proven that $124,343 is just the right amount to allow the student to withdraw $50,000 a year for 3 years if the student is able to earn the 10% interest. And let's take a look at one last example here. We have Minus Company. They purchase some artwork. So Minus Company makes a deal with the artist, and the deal is Minus Company is going to pay the artist $8,000 a year for 3 years. Once again, the payments being made at the end of each year, so this is another ordinary annuity situation. This time we'll assume that the appropriate interest rate is 8%. And the question that we want to answer here is, what should Minus Company consider to be the purchase price of that artwork? Well, in total, Minus Company is paying $24,000 over that 3-year period. Is the artwork worth more than $24,000 or less? You know the answer has to be less than $24,000 because that $24,000 really was including interest at 8%. If you go to the table and look up the factor for present value of an ordinary annuity for 8%, 3 years, you'll come up with this factor, 2.5771, and if you multiply that times the annuity amount, you can see that we've determined the purchase price of the artwork to be $20,617. The difference between the $20,617 and the $24,000 would be the interest that Minus Company paid to the artist. Optionally, you could use Excel. Notice that we're using the same present value formula that we used before, and your inputs would look like this. Try these inputs in Excel, and you should get the same answer that we computed up here. Another common situation in annuity problems is that you may know the present value of the annuity or the future value of the annuity, and you may know the interest rate and the number of compounding periods. What you don't know and what you would like to know is the amount of the annuity payments. So these are problems where you are solving for the annuity amount. When the annuity amount is unknown, notice here on the timeline, the payment amount is the question. And you have to make a determination as to what you do know. Do you know the future value of that annuity, or do you know the present value of that annuity? Let's read through an example. So here we have Birdley Inc. They borrow $300,000, 5% interest rate. Birdley will repay this amount by making 3 annual payments at the end of each period. So here's the payments that we're looking for. What is the amount of payments that Birdley will need to make to pay off the loan? Well, what do we know? The future value of those 3 payments or the present value? In this problem, Birdley's borrowing the money today, so we know the present value of those payments. Let's just think logically here for a minute. If there was no interest, what would the payment need to be? Well, if there was no interest, the payment would be $300,000 divided by 3, or $100,000 a year. Since there is interest, the payment's going to need to be more than $100,000. So that'll be our logic check after we do the computation. I would set it up like this. You've used this formula a couple of times already, just in the last few minutes. If you want to compute the present value of an annuity, you take the annuity amount, the payment, and you multiply it times the present value of an annuity factor. In this case, we know the answer. We know the present value of the annuity, $300,000, and we can look up the factor. If you look up the factor for 3 payments, 5%, it's 2.72325. So if you take 300,000 and divide by that 2.72325, you're solving for the payment amount. The payment will be $110,163, and that agrees with our logic a few minutes ago. We knew our answer would have to be greater than $100,000. So 3 payments of $110,163 is just the right amount to pay off that $300,000 loan and include interest computed at 5% annually. The method that we just used is, if you're solving for an annuity amount and you know the present value of that annuity, divide the present value that you know by the present value of an annuity factor. So this is one of those occasions where you need to divide to solve your time value of money problem. Now let's try another one here. So similar example, but notice the difference. Here we have Beasley Inc. They want to save $300,000 so that the company can have a corporate retreat in 3 years. Once again, our interest rate is 5%. And we're asking, how much will Beasley need to deposit at the end of each year for the next 3 years to accumulate the $300,000? So we know that the payment amount is the unknown, our annuity is the unknown, and in this case, do we know the present value of those payments or the future value? We've been told that they want those payments to grow in the future to be $300,000, so we know the future value of the annuity. We solve it similar to how we did it with the present value situation. We know the future value of the annuity is computed by taking the annuity amount times the future value of an annuity factor. So $300,000 is equal to the annuity amount times 3.1525. To isolate the payment on the right hand side here, we divide each side by the factor, and our answer is $95,162. And this makes sense. If Beasley could not earn any interest at all, they'd have to deposit $100,000 a year. But since they can earn interest, it makes sense that the annuity amount would be less than $100,000. And in fact, if we did a little amortization schedule, we could prove that 3 payments of $95,162 would grow to be $300,000 in 3 years if it was earning 5% interest. In this case, we divided what we knew, and it was the future value of an annuity, by the factor for what we knew. We divided by the future value of an annuity factor. If you want to use Excel to solve for the annuity amount, you'll want to use the payment function. So this is what the payment function would look like. You're already familiar with our input types here. As you recall, in the Birdley example, we knew the present value of the annuity. So PV here would be minus $300,000. You would put 0 in for future value and 0 in for type. Put in your rate and number of compounding periods, and Excel will compute the annuity amount for you, and it should match what we computed earlier. In the Beasley example, we knew the future value of the annuity. So in that case, replace PV with the 0 and replace the future value with the minus 300,000, and you should get the same answer that we got a moment ago for the Beasley example. And as you can see at the bottom here, just a quick note, you can use the rate function and the number of period function when you have an annuity situation, just like you did when you had single sum situations. Well, let's change gears again, and now let's talk about annuity due situations and how that changes our computations. When payments occur at the beginning of the periods as opposed to at the end of the periods, we have annuity due situations. So notice in this present value of an annuity situation, payments occur at the beginning of each one of these periods. Same thing in the future value situation. The timing is important, and the factors will be different because whether this first payment is made here, second payment here, and third payment here, or the payments happen here, here, and here, changes the amount of interest. So it's very important to identify whether you have an ordinary annuity situation or an annuity due situation. Let's think back to one of our previous problems that we looked at together. We had that accounting student that wants to save money. The student's making $10,000 deposits at the beginning of each year for 3 years. The interest rate is 10%, and we're asking the question, how much will the student have after 3 years? We did this problem before, and the student was making payments at the end of each of the periods. Now we're changing the payment schedule. They're happening at the beginning, and what do you think is going to happen? What's the future value of these payments? Is it going to be greater or less than what we computed before? Well, it should be greater because now each payment is earning interest for one additional period. This first payment now is going to earn interest for a full 3 years. The second payment is going to earn interest for 2 years, and the third payment gets to earn interest for 1 year. So each payment is earning interest for an additional period. We really use the tables the same exact way once we correctly identify a situation as involving an annuity due. So you'll want to make sure that you pick the right annuity table, use the future value of an annuity due table. In this case, it was 10%, 3 years, so the factor is 3.641. You multiply that times the annuity amount, and the student would accumulate $36,410 over the 3 years. When we did this problem As an ordinary annuity, the payments only grew to $33,100. So you can see the impact of that additional period of time for each payment to earn interest. You need to change your input just a little bit if you're using Excel to solve these problems. When there is an annuity due, type is 1. If it's an ordinary annuity, type is 0. When it's annuity due, type is 1. Try this in Excel. Get the function and replace with these facts down here, and you should get the answer that we got a moment ago of $36,410. Let's do the same thing with a present value example. So one of the present value examples we did was our accounting student who inherited some money. She wanted to set some aside so that she could withdraw $50,000 a year for 3 years. When we first did the problem, the student made the first withdrawal at the end of the first year, the end of the second year, and the end of the third year. Now we're going to assume that she needs to make those withdrawals at the beginning of each year. So payment 1, payment 2, payment 3. And as you can see, each payment now will be discounted for fewer periods. If you go to the present value of an annuity due table, you'll see the factor of 2.73554, multiply it times the annuity amount. You'll solve for the amount that the student needs to deposit as $136,777. So she needs to deposit $136,777 in order to be able to withdraw $50,000 for 3 years with this timing. Notice that more money is needed now than it was when we did this problem as an ordinary annuity. When we did it as an ordinary annuity, the student only needed to deposit $124,343. There needs to be more money deposited up front now because that first withdrawal is happening earlier than it did when it was an ordinary annuity. So less interest is being earned on the money deposited in that account. We can do the artwork example as an annuity due as well. Remember this example? Minus company buys artwork. The artist agrees to accept $8,000 per year for 3 years. This time let's assume that minus company is going to make the payments at the beginning of each year instead of at the end of each year. If you try it in Excel, you would type the function in like this, and your answer will come back as $22,266, which is more than what we got when we did this as an ordinary annuity. Now we're saying that those 3 payments of $8,000 a year are worth more than they were before. That's because the payments occur earlier, so less of the amount being paid to the artist is interest, and more of it is for the value of the artwork. So now we would compute that that artwork must be worth $22,266. We use time value of money in lots of different places in financial accounting. So you can read through this list. These are some of the examples where we need to consider time value of money. You'll see them heavily in this course in the leases section, leases receivable, leases payable, bonds, and pension obligations. But we'll see it in other areas as well. The last 2 slides on the handout, I'll just show them here to you now, but they're more valuable if you print the handout. It's just a summary of the formulas that are used to compute the factors in the tables. So these are the formulas that compute the factors in these related tables, and there's 2 more here on the last slide.